Okay, we're going to continue on here to chapter 9. So in this chapter, we're going to talk about a really important sort of calculation. Was referred to as stoichiometry. And it really does sort of put together some of the topics from the previous chapters, more specifically sort of the grams and the moles and the molar mass and our equations and balancing equations. So what we're going to talk about here today is stoichiometry, which basically involves doing calculations based on the balanced equation. And you can figure out things like, if you started with a certain amount of reactants, how much products you should make. You could also figure out if you produced a certain amount of products, how much of the reactants that you would have started with along the way. So stoichiometry is really used to sort of answer those questions. And it really does involve two of those concepts that we talked about in previous chapters, kind of converting our grams to moles and obviously molar mass. So one really important relationship that we will use in this chapter, and I think saw the slide in an earlier chapter, maybe when we were talking about the balancing equations. Looking at a balanced equation, it does give us some information about both the reactants and the products there. And we can use a very simple relationship from the balanced equation, which are the coefficients there. And we could say that for 2 molecules of H2, it reacts with 1 molecule of O2 to form 2 molecules of H2O. Really sort of the relationship that we use the most, and especially with stoichiometry, is what's sometimes referred to as the mole-to-mole relationship. And that's found the same way. It is just the coefficients. So really this relationship here is really pretty much the basis of stoichiometry and its calculations. And it is sometimes, again, referred to, as I mentioned, a mole-to-mole relationship. And sometimes people get really confused as to maybe where those numbers come from, but it really is just simply the coefficients in the balanced equation. So again, looking at the coefficients there from H2, we could say we have 2 moles of H2 react with 1 mole of O2. Obviously, just like in chemistry, if there's no number written there, it's assumed to be 1, and 2 moles of H2O. So really in stoichiometry, that is the relationship that we're going to use. This is the idea of conservation of mass, as we talked about when we talked about balancing equations. So clearly, we do not lose any elements along the way in a chemical reaction. The only thing that happens is all the bonds are broken on the reactant side. They basically remake bonds on the product side. So again, if you started with 6 carbons, you should end with 6 carbons. And the molar mass of carbon on both sides of the arrow is going to be the same. So that's the idea of the conservation of mass. So let's talk a little bit about stoichiometry here and really some of the things that we look at. As I mentioned, using that sort of balanced equation and a mole-to-mole is what's referred to as stoichiometry. So you might ask, like, why do we need to do that? The reason we need to do that is in these type of problems or stoichiometry type problems, you're typically given information about somebody in the equation, either a reactant, either a product, and you're not really interested in that particular substance. You're interested in somebody else in the equation, maybe another reactant, maybe another product. So really, you could boil down stoichiometry to pretty much, it is really just a conversion factor. So instead of looking up in a table the conversion factor, where we find the conversion factor is really from the balanced equation. And that allows us really to relate everybody in the equation to each other by doing that. So as I mentioned before, if we know how much reactants we started with, you could figure out based on the equation how much products you should make. And if you actually know how much products that you made, you could also figure out how much reactants you would have had to start with to make those products. Another really important thing to keep in mind as we do sort of stoichiometry problems is sometimes, if we have the reactants there and our products here, sometimes people think that it always has to be sort of a relationship between reactants to products or products to reactants. And you could do stoichiometry problems where you relate, say, reactants to products or products to reactants. You could also do stoichiometry just between reactants. So if you had a couple of reactants, you could actually stay on the left-hand side of the arrow and do these type of calculations between the 2 reactants. And you could also do stoichiometry between 2 products. If you had multiple products, you don't necessarily have to cross the arrow, and you can kind of do a relationship between 2 products. So sometimes people think you always have to do sort of the relationship from the reactant to the product. and you don't. So you could do the stoichiometry with anybody really in the equation. You could go reactant to product, you could go product to reactant, you could our relationship between product and product. So it works for basically everybody in that equation using those coefficients. So when we talk about units in typical stoichiometry problems, they really can be anything. They can be any units that you want or are given. I would say most commonly, these are going to be the two units that we'll see probably the most in basic stoichiometry problems, which are grams to moles. Later, we will definitely see it when we talk about gases and do stoichiometry involving gases. It could be liters. Later on as well, we will see stoichiometry involving solutions. So molarity and concentrations are used a lot in calculations involving stoichiometry. But a lot of the basic sort of stoichiometry problems, like we'll be doing probably in this chapter, involves grams to moles. And a very important step in a lot of the process is to take grams and convert them into moles. And a reminder that to do that, that is the molar mass from the periodic table, right? So if you need to convert somebody from grams to moles or even moles to grams, which is also used a lot in this calculations, you want to go to the periodic table, get the molar mass to grams per mole of that particular substance to do so. So the mole method here is, again, as I've been mentioning, really just the coefficients from the equation. And that's why it's really important always to have a balanced equation. Pretty much if you do not have a balanced equation, your calculation is going to be wrong in most cases. So it all really starts always with the equation. You want to make sure that it is balanced. And if you didn't balance it and they gave it to you, you want to really make sure that the equation actually is truly balanced. For basic stoichiometry problems like we're going to talk about here up front, and how you know it's sort of a basic stoichiometry problem is, frankly, they just give you one piece of information. So they just tell you either something about a reactant, they tell you something about a product, and that's all the information that's really given to you. There's really kind of 4 steps. There is 5 steps up here. The first step here, you probably won't run into too often, but it does happen. And the first step is sometimes you may be given a problem where everything is given to you in words. So as we've talked about, what you want to do when you have problems where everything's in words, you want to make sure that you write the proper chemical formulas first before you balance the equation. So you want to make sure you get everybody down with the correct formulas. Maybe if you have to predict something on the right-hand side of the arrow, you predict it properly. Is it a double displacement reaction, a single replacement reaction, whatever it may be? Remember that you just want to do it like you were doing sort of nomenclature, put everybody together properly. Once you have the proper sort of formulas down, that obviously is your unbalanced equation. Really, in most cases, this is going to be probably your first step, which is to actually balance the equation. And again, if it is given to you the equation and you see coefficients, you should still probably take a look at it really quick to make sure. I would say probably in most cases that's going to be a balanced equation unless somebody's trying to trick you. But you should always take a look at it just to make sure. If you definitely see an equation, there's no coefficients, you should definitely take a pretty good look at it to make sure that it is balanced. And if not, make sure that you do balance it. The next thing that you want to do is typically whatever they give you, you want to convert to moles. So usually the end part of that step is grams to moles. And that, again, is the molar mass that we want to use from the periodic table to do that conversion, which gives us grams per mole, right? Now, it is very common that you're given something in grams. It's also might be common that you're given something in some other unit. So whatever unit they give you, you got to pretty much get them to grams, then use the molar mass from the periodic table to go from grams to moles. So that is sort of the order at which you want to do it. Once you get there and you got whatever they gave you into moles, now you're going to actually get to the stoichiometry part. And the reason we need to do the stoichiometry part is, frankly, whatever they gave you is not what you're interested in for the answer. You're interested in somebody else in the equation. So again, we need some conversion factor that allows us to go from whatever they gave you to what we're looking for in the end. And again, like I mentioned, instead of like looking it up in a table, we actually use the balanced equation to get that relationship. And it is simply the mole-to-mole relationship, which is the coefficients. Once you do sort of the third step, really, in most cases, the fourth step is to take those moles and convert it to some other unit. Now, if you successfully do sort of the third step correctly here, you should always be in moles. Otherwise, you did something wrong. And maybe they want grams at the end. So it's very common at the end to use molar mass one more time to convert it from moles to grams. But they could want any type of unit. So you might have to do multiple conversions along the way. So like I said before, in a lot of cases, you won't have to worry too much about this first step. And really 4 basic steps to stoichiometry problems: balance the equation, convert to moles, do the mole-to-mole relationship from the equation, and convert moles to some other unit. Pretty much all basic stoichiometry problems boil down to those 4 steps. You should always do them in order, and you will hopefully get the right answer as long as you don't make any calculation error. You should also avoid doing some weird things that people sometimes do, which is undo things. So what I mean by that is, if something is done for you, you just go on to the next step. So for example, if you're given something in moles to begin with, don't unconvert them to grams and then reconvert them back to moles. It's already done for you. Just kind of go forward. Sometimes people do those weird type of things. And there's always sort of these 4 steps. Any questions on that there? All right, so let's take a look at an equation here, and let's talk about how we really get these sort of relationships. So as I mentioned, pretty much the balanced coefficients, which is why it pretty much needs to start with a balanced equation, gives us those relationships. From this one equation here that is balanced, we could come up with a number of different relationships. We could say that for every 2 moles of CO, and that comes from the coefficient, we could react it with 1 mole basically of O2, which is O2's coefficient. We could also say that for every 2 moles of CO we toss in there, we will get out 2 moles of CO2 in this equation. And we could say for every 1 mole of O2, we get out 2 moles of CO2. These are 3 different, what is referred to as being stoichiometrically equal to each other, and equalities that we could get from this equation. They are clearly not equal to each other, like 2 does not equal 1 in terms of a number. They are equal to each other in terms of like proportion that you need to throw in there for this reaction to take place. So it's kind of like when you make cookies, you got to throw so much flour in, right? So much chocolate chips, so much butter to get like 12 cookies out. It's the same idea here. So that's sort of how they're equal to each other in terms of proportion. They are not equal to each other in terms of numbers. Now, because they are technically referred to as equalities, you will remember from when we talked about basic conversions, from any equality that you have, you could actually write 2 conversion factors. So for each of these sort of equalities, you could write 2 conversion factors. You could say that for 2 moles of CO, I have 1 mole of O2, or you could flip it around the other way. 1 mole of O2 gives me 2 moles of CO. For the middle guy, you could say 2 moles of CO gives me 2 moles of CO2, or 2 moles of CO2 gets me 2 moles of CO. And for the last one, 1 mole of O2 gives me 2 moles of CO2, or 2 moles of CO2 gives me 1 mole of O2. So from this one equation here, we have basically 3 equalities that we could get from it. And we actually have 6 different conversion factors that we could use in the problem. Will we use all 6 of these? The answer is no. You're just going to use pretty much the one that you need. But you do have all these available to you to use in a problem. And in most cases, most problems, you're just going to use one. First off, any questions on how I got those relationships? So let's see sort of how this works. So for example, let's just say here that let's say in this reaction here, we produced 20.5 grams of CO2, and we want to know how many grams of O2 did we start with. So we're going to do this problem. We're going to run through the basic stoichiometry steps like we've been talking about. And again, I know it's a basic stoichiometry problem because frankly, I'm just given one piece of information. So the 4 steps again is to balance the equation, convert to moles, do the mole to mole relationship, and lastly, convert our moles to some other unit. All right, so obviously step number 1 there is done for us. We have the balanced equation, which is right there. Step number 2 is I have 20.5 grams of CO2. Do I need to convert that to moles? And I do, right? Because it's in grams, we need moles. That also means we need to go to the periodic table and get the molar mass of CO2. So the molar mass of CO2 is 12.01 grams per mole for the carbon, plus 2 times 16. For our oxygens gives us a molar mass of 44.01 grams per mole. So really the second step that we're going to do here is convert our grams to moles. So starting with our 20.5 grams of CO2, using the molar mass as a conversion factor. Going to put the grams on the bottom so that they cancel. Moles of CO2 up on top. Grams will cancel. And this will get us 20.5 divided by 44.01. Going to give us here 0.4658. We'll call it moles of CO2. Now, I'm not going to round too much here because I'm going to continue on with the calculation. So again, you might want to take a few digits. At this point, we have now converted into moles, which is what we need to do. And really, the reason we need to convert to moles is because step number 3, we need to use the mole to mole relationship. So everybody's got to be in the right units. How do we find the proper relationship? We go to the balanced equation and we find the 2 things we're interested in. And one thing we're interested in is what they gave us, which in this case was CO2. The other thing we're interested in is what we're trying to find. In this case, we're trying to find oxygen, which is O2. So from that equation, as we did earlier, we see that for every 1 mole of O2, we have 2 moles of CO2 is produced. That gave us 2 conversion factors that we could use. We could use the one here on the left, and we could use the one on the right. Which one should I use in this case? I want to get rid of CO2 and end up with O2. I should use the conversion factor on the left, right? That's going to allow us to do it. So this is the big stoichiometry move right here. It's going to the equation, finding the mole-to-mole relationship as a conversion factor. So continuing on for the 3rd step here, I'm going to take my moles that I calculated. I'm going to use the stoichiometry relationship from the equation. I'm going to put the 2 moles of CO2 on the bottom, 1 mole of O2 up on top, and that's the big stoichiometry step right there. We're going to take it and divide it by 2, and that is going to give me 0.23290 moles of O2 in this case. Again. 3290. Okay. That takes care of the stoichiometry part and step number 3. In this case, we do need to do step number 4 because the end unit that we're looking for is grams. So I do need to convert now my moles into grams, and I do need to use the molar mass. One really important thing is at this point, I should use the molar mass of what substance? Of oxygen. So sometimes people get confused and they still use the CO2. You do have to remember at this point that you've now converted into oxygen. So you want to use the molar mass for that. So for oxygen, that's obviously 2 times 16, which is a 32 grams per mole. So we will use that as our last step here. In this case, the 32 grams will go up on top as we want to end up with grams. And moles will go on the bottom so that they cancel. And taking this and timesing it by 32 will get us something like 7.45 grams of O2 in this particular case. That obviously would be step number 4 that we did over here. First off, any questions on it? Yeah. Why was it what? 32 grams per mole? That's the molar mass of O2. So from the periodic table, 2 times 16, yeah. Other questions? So it is the same 4 steps here. And again, step number 1, balanced equation. Step number 2, convert to moles. Step number 3, mole to mole relationship. In this case, step number 4. A couple of other things here just to talk about it. In terms of sig figs, this is really the only number we had in the problem, which had 3 sig figs. That is why I rounded to 3 sig figs at the end of the calculation. The other thing is, if you want to, you can all in one calculation. You could do this guy to this guy to this guy without getting an answer in between, and it's perfectly fine to do. If you do get an answer in between, like I did here, try not to round too much until the end. Otherwise, again, if you round a lot along the way, you might end up with the wrong answer. So I took it to a few digits, and to be truthfully honest with you, I took the entire number that was in my calculator through all the steps. So again, if you want to do it all in one calculation, you can. Or if you do get an answer, try not to round too much. How I got where I got the relationships from? Yeah. So so in actually here, let me just do it. I think I got the equation here. There you go. All right. So from this equation, it really just comes from the coefficients. So that's a 2, nothing written means a 1, and something written here. And it's really nothing more than just the coefficients. So for all those guys, basically we could say that there are 2 moles of CO from there. You got to throw in 1 mole of O2. You could also say for every 2 moles of CO that you toss in there, you got to also get out there 2 moles of CO2. And for every 1 mole of the O2, you get out 2 moles of the CO2. So that is where the relationships come from. And that's why it's extremely important in this type of calculation that you always start with a balanced equation, because if you do not, then you're going to have the wrong sort of mole to mole relationship. And then obviously the conversion factors came from each of those. Yeah. Other questions on that? The other really important thing to remember as well is when you're doing molar mass, a mistake that sometimes people will make. For example, I did the molar mass of CO2 earlier, and sometimes people will go, well, there's a 2 there. I should add that to my molar mass, and you should not. So whenever you calculate the molar mass from the periodic table, regardless of the coefficient that you see here, it should only be done based on the formula by itself. So that is always the way that you calculate molar mass. That is another very common mistake that people make. They use the coefficient twice, basically, in the calculation, and you should not do it. So molar mass only from the formula. The coefficients are taken care of when you do the stoichiometry part of the calculation, so you shouldn't combine those two. And again, that's a very common mistake that sometimes people will make. Other questions on that there? All right, let's take a look at one here. Why don't you give this one a go? Lithium metal reacts with water to form hydrogen gas and lithium hydroxide. We want to know how many moles of hydrogen can be formed by the reaction of 5.32 moles of lithium with water. So I'll help you out here to begin with. This is one where I talk about, not too common, but it does occur that they give you everything in words. They really don't give you sort of the equation. So remember that if we do to form hydrogen gas, another very common mistake is people will just write H. Gas, oxygen gas, right? Fluorine, chlorine, bromine, iodine, and oxygen and nitrogen, they're all diatomic molecules. So you want to make sure you get the formula. And lithium hydroxide, which is LiOH. All right, so again, what I did there is I was not concerned about balancing the equation. I just wanted to get the right formulas. Now you should balance it. So follow those 4 steps, balance the equation, convert to moles, do a mole to mole relationship, and moles to some other unit. All right, take a few minutes here and see what you come up with. Okay, let's take a look. So again, we're just going to follow our steps here. We now have the right equation down there, but it is unbalanced. So we want to make sure we balance it up first. So to do that, I think you need some 2 there, maybe a 2 there, maybe a 2 there. So that would be our first step there, which would be to balance it up. We got 2 lithiums on each side, 4 hydrogens and 2 oxygens in this case. At this point, the next thing we want to do is convert to moles. We know this is a basic stoichiometry problem because, frankly, we are only given one piece of information here. And it is actually already in moles, which means we don't need to do that step because it's already done for us. So once again, do not undo it and redo it. So we're really now down to actually step, which things we're interested in. Again, in this time, we are interested in whatever they gave us. So in this case, they gave us lithium, which is here. And we are interested in what we're trying to find, which is hydrogen, which is there. And from the equation is where we're going to get that relationship. And again, it's nothing more than the coefficients. So we could see from the equation that we have 2 moles of lithium, which again is our coefficient. Gives us 1 mole of H2, which is the coefficient here because there's nothing written. That would obviously give us 2 conversion factors we could use. 2 moles of lithium over 1 mole of H2, or 1 mole of H2 over 2 moles of lithium. So that is where we want to pick up step number 3, which in this case is 5.32 moles of lithium. I should use conversion factor on the left or the one on the right in this case. We should use the one on the right as we want to get rid of lithium and end with hydrogen. So we're going to do our stoichiometry part here, 2 moles of lithium and 1 mole of H2. That is going to get rid of our lithium. We're going to divide it by 2. Looks like a 2.66 moles of H2 in this case. In this particular problem, we actually do not need to do step number 4 because we're actually looking for moles. So we're right there. If I did want grams, what would I need to use? I would use the periodic table and get the molar mass of H2 in this case, right? And then I could do the last step. So we don't need to do it in this particular case. Question on that one there. All right, so that also shows you might not have to go all the way to step number 4, but a lot of times you do. But again, it is 1, and number 2 was done for us. Number 3 was done, and number 4 here we actually did not need to do in this particular case. Any questions on that there? Now, by the way, what we just got here is a product. And based on the equation, what this says is if I threw into this reaction 5.32 moles of lithium, everything went perfect. Students dropping along the way, no side reactions. You should get out 2.66 moles of hydrogen. That is what is referred to as the theoretical yield. Yes, sir. Yeah, so this would be solid, right? With this, what lithium metal would be. This would be liquid. Hydrogen is obviously a gas, right? And this would probably be aqueous based on solubility rules. Yeah. Other questions on that? Okay. All right, so let's take a look at another one here using the same equation. That is this one, I think. So using the same reaction, in this case, we want to know how many grams of hydrogen would we produce in the complete reaction of 81.75 grams of lithium. Here's some numbers that might be helpful. Lithium from the periodic table, 6.941. And hydrogen, 1.008. So once again, follow those 4 steps, balance the equation, convert to moles, mole to mole relationship, and moles to some other unit. All right, take a few minutes there, see what you come up with. Okay, let's take another look here. And again, we're just going to follow the steps. So balance equation we did previously. So that's obviously all taken care of. We know this is a basic stoichiometry problem because frankly, we're only given one piece of information, and that is 81.75 grams of lithium. That also tells us that we do need to do step number 2 here, which is convert the grams to moles. So that is where we're going to start. We're going to go with 81.75 grams of lithium. Our second step here. And using the molar mass from the periodic table, that's 6.941 grams per mole of lithium. The grams of lithium will cancel. And again, if you get an answer at this point, you got 11.7778 moles of lithium. Once again, I'm not going to do a lot of rounding here until the very end because I'm going to get answers after each step. That is step number 2, check off. At this point, we're going to do step number 3, which is the big stoichiometry step. So we're going to look at our relationship. So it is the same relationship. We were given something about lithium, and we are interested in our hydrogen. So once again, that gives us 2 moles of lithium from the equation, gives us 1 mole of hydrogen, gives us our same 2 conversion factors that we could use. And in this case, we are going to use pretty much the same one as we did last time. So in this case, we will use our guy here on the right. And that's going to be the stoichiometry part. That's really the conversion factor that's going to allow us to go from lithium, which we're really not interested in, to hydrogen. So again, we're just kind of getting the conversion factor from the equation. And to do that, we do want lithium on the bottom so that it cancels. And we want hydrogen up on top there so that we are left with that. And if we do that, we're basically dividing it by 2. I'm going to write it underneath here to the left. 5.8889 moles of H2 in this case. And obviously that would be step number 3. In this particular case, we do need to do step number 4 because we're not looking for moles as our final answer. We are looking for grams. So we do need the molar mass of H2 in this case, remembering that we have converted over to H2. So we would go back to the periodic table for H2, and that would give us 2 times 1.008. And that's like 2.016 grams per mole. Using that for our final step here, the grams go up on top. Moles on the bottom. Once again here, I just used the equation or formula for the molar mass, and that would get us times 2.016. 11.87 grams of H2 in this case. I went to 4 sig figs based off the only number really in the problem was 4 sig figs in this particular case. So again, what this number means is if you dumped into this reaction 81.75 grams of lithium, everything went good, no side reactions, nothing dropped along the way. in theory, you should get out 11.87 grams of hydrogen, which once again is why this is referred to as the theoretical yield. The theoretical yield is based on the equation, based on your starting amount. It's like perfect ideal conditions. This is theoretically your maximum amount of product that you could produce. You could only have a theoretical yield for a product, yeah, because that is what is made as a result of reaction. So no theoretical yields or anything like that for reactants. It has to be a product. Any questions on any of those steps there? Once again, you could just do it all in one calculation, this guy to this guy to this guy, again, without getting the answers in between. That's perfectly fine as well. All right, let's take a look at another one here. These are the ones we did, so hopefully you got the same answers. That would be good. That's good. All right. All right, let's try this one here. If you started with 765 grams of C6H12O6 and it's consumed by the body, what is the mass of CO2 produced? And we are looking for grams of CO2, basically. Some helpfulness here. Carbon is 12.01 on the periodic table. Hydrogen 1.008. And our friend oxygen still 16. So again, follow those 4 steps. All right, let's take a look. So again, we're going to want to balance the equation. In this case, I do see coefficients. You should, it probably is going to be balanced if you do see coefficients in there. But you should always take a double check just to make sure. In this case, it is. I know, again, this is a basic stoichiometry problem because I'm given just one piece of information there. That also means that since I was given to it in grams, I will have to convert it to moles. So we would go to the periodic table. We're going to add up all the parts here. So we got 6 times our carbon plus 12 times our hydrogen's mass from the periodic table plus 6 times our oxygen's mass from the periodic table. And that's going to give us a molar mass of 180.2 grams per mole. Once again, usually molar mass, you round the force and figures is really where you take it. So we're going to use that number there, obviously, to do our conversion, our second step, which is convert to moles. The 765 grams of C6H12O6. In this case, we want the grams on the bottom so that they cancel. And once again, we calculated the molar mass based solely on the formula. Have nothing to do with the coefficient in the equation. So our grams here will cancel. If you did get an answer at this point, that answer would be about 4.24632 moles of C6H12O6. The next thing that I want to do is actually the stoichiometry part. Although we are given C6H12O6, we're not interested in that. We're actually interested in CO2. So going to the equation here, we want the relationship between this guy and this guy. And what we see from the equation is for every 1 mole of the C6H12O6, we produce 6 moles of CO2. That again will give us our 2 conversion factors that we could use. In this case, we want to use it where the C6H12O6 is on the bottom. So that's what we'll do. 1 mole of C6H12O6 on the bottom gives us 6 moles of CO2. That is what is going to allow us to go from what we're not interested in this case to what we are interested in. And really, again, stoichiometry is just a conversion factor. So those guys are going to cancel out. We're going to basically times it by 6 in this case. I'm going to put the answer here to the left, 25.47792. Once again, I'm not rounding too much here to the end. That takes care of step number 3, which would be there. What is left in this case is we do need to do step number 4 because we're interested in grams as a final answer, not moles. So we do need the molar mass. And again, at this point, we are at CO2. So we need the molar mass of CO2. And we did that earlier, 1201 grams per mole, plus 2 times 16 for our oxygens. Once again, just using the formula only for molar mass, that is 4401 grams per mole. We're going to use that as a conversion factor here. Grams going to go up on top, 4401 grams of CO2 in a mole. The moles will cancel times 4401. Going to give us about 1121 grams of CO2. Thinking about maybe significant figures, the only number right there is 3 significant figures. So maybe a final answer of 1120 grams of CO2. And that obviously would be step number 4. Any questions on those steps? Hopefully you can see a pattern here that it is the same 4 steps. Just follow the steps there. Should get you to the end. This also means that if I did this reaction here, dumped in 765 grams of it, everything went perfect. What I should get out from my theoretical yield is about 1120 grams. Any questions on basic stoichiometry problems? All right, and again, like I said, you could do this all in sort of one calculation without getting the answers in between. And once again, if you do get the answers in between like I've been doing, take it to a few digits there. Don't do too much rounding along the way. So let's talk a little bit about what happens when we got a little bit more complicated of a problem. So let me find it here. That's one we just did. I'm going to actually skip this example. So if you want an extra practice problem, you could do that one. Maybe we'll come back to it when we get a chance. So the next thing I want to talk about, though, is what's referred to as limiting reagents. And sometimes they're called limiting reactants. And whenever you do any type of reaction, there's always going to be pretty much a reactant that gets used up first, or a reagent that gets used up first. And that's what's known as the limiting reagent. So the limiting reagent, or again, sometimes referred to as reactant, is the one that gets used up first in a reaction. And there's another reagent, as we'll talk about on the next slide there, which is known as the excess reagent. And you have plenty of that guy. You have so much of the excess reagent that, as we'll talk about, you actually have some left over when the reaction is done. Why is limiting reagent sort of important? It's important because if we just take a very simple example of, we take a reaction where we go A plus B makes A and B. And let's just say, hypothetically speaking, that A is our limiting reagent. When I run out of A in this reaction, would I be able to make any more product at that point? I would not, because in this case, I need an A and a B basically to make the product. And that's why limiting reagents are really important. It is always the one that determines how much product you can make, because as soon as it runs out, there's like no chance that you can make any product at that point. So limiting reagents is always the one that basically determines how much product you produce. Again, as I mentioned before, the excess reagent is the one that you have plenty of, and you still have some left over when the reaction is done. Kind of like, I think if you ever bought hot dogs and hot dog buns, I think they sell you like 8 hot dog buns and like 10 hot dogs, right? So you're kind of always short. So you always have to buy another package of buns that you'll never use. So, you know, obviously if you put them together to make hot dogs, the limiting reagent would be the buns, right? The excess reagent is we got a couple of hot dogs left over when it's all done, right? So you could even figure out how much of that excess reagent is basically left over. So that excess reagent, as I mentioned, is the one that you have plenty of. And very common questions that you're asked with limiting type reagent problems is, you know, how much product that you would produce, and that would be based on the limiting reagent. And you're oftentimes asked how much of that excess reagent you have left over. So those are two very common things that you're sometimes asked in these type of problems. How do you know it's a limiting reagent problem? You know it's a limiting reagent problem because you have enough information given to you in the problem that you could get to moles of each reactant. So if you have some type of problem where you're like, oh, I could just convert to moles of each reactant, that is a big hint that it is a limiting reagent problem. If you think about the examples that we did previously, we were only given really one piece of information. Maybe it's a reactant, maybe it's a product, whatever it may be. But in a limiting reagent problem, figure out which one is the limiting reagent is you will always be given enough information, whatever that information is, that you could do some conversions to get it to moles without doing anything else. And that definitely is a limiting reagent problem. So an example here, if we're making sort of workout buddies, we got guy workout buddies, girl workout buddies. Obviously, we need one of each. So we could see we need one guy and one girl, one guy and one girl, one guy and one girl. We're out of guys, which means we cannot make any more product at this point. That means that the guys in this case would be our limiting reagent. The girls here would be our excess reagent. And like I said, we could even figure out, in this case, we would have 2 left over, right, when the reaction is done. So you could even figure out how much that you would have left over. How do you solve for limiting reagent problems? There are actually many different ways you could kind of do it, or a few different ways. We're going to talk about a way which really follows what we've been talking about in terms of stoichiometry. You still follow the same 4 steps of balance the equation, convert to moles. And right around here, you have to do your little calculation, which we'll talk about as to how to figure out which one's the limiting reagent. After you figure out which one's the limiting reagent, you always use the limiting reagent and continue on, which would be then the mole-to-mole relationship between the limiting reagent and your product. And finally, your moles to some other unit. So it's basically the same 4 steps, just kind of got to stop halfway through, do a small little calculation to figure out which one's the limiting reagent, and then you basically pick up with the limiting reagent and continue on with the calculation. All right, so let's take a look at how to sort of incorporate that into what we've been talking about. Let's take this reaction here, and let's say that in this reaction, we are starting with 4 moles of sulfur and 20 moles of F2. So that is the moles of each of our reactants. That right there is a very big hint that I have moles of each reactants, or I'm able to calculate moles of each reactants. This is a limiting reagent problem. So because I have the moles of each one, I know this is a limiting reagent type problem because I could get the moles of each of them. So what that means is we're just going to follow the same steps. We're going to balance the equation, which it is done already. We're going to convert to moles, which it is done already, so we don't have to do that part. And again, if we did, you use the molar mass like we did before. So now we're at the part where we recognize that it's a limiting reagent problem. We need to determine which one's the limiting reagent. So this approach basically does a small calculation to figure out if I want to use up one of my reactants, how much of the other one I need to put in there. So just to illustrate it here, we are starting with, in this case, 4 moles of sulfur and 20 moles of F2. So what I'm going to do now is a calculation to help me figure out which one of these 2 is the limiting reagent. So what I'm going to do is, if I want to use up all of the moles of sulfur I started with, how many moles of F2 is needed? That's basically what this calculation is. So I'm going to take the starting amount of S in moles, which is 4 moles of S. Going to the equation, I'm going to find a relationship between those 2 reactants. And that is 1 mole of sulfur gives me 3 moles of F2. That gives us our 2 conversion factors we could use, just like we were doing previously. So 3 moles of F2, 1 mole of sulfur. At this point, we want to use the conversion factor here on the right. So I'm just going to do this small little calculation here. 1 mole of sulfur, 3 moles of F2, moles of sulfur cancel, 12 moles of F2 is needed. So again, that calculation basically saying I want to use up all the sulfur, how much F2 I need to toss in there. This is where we can figure out which one is the limiting reagent. I want to now compare my calculation, which is I need 12 moles of F2, and I am starting with 20 moles, right, of F2. Do I have enough moles of F2 to actually do that? I do, right? I only need 12, and I would need 20 that I started with. I said that backwards. I have 20, and I only need 12 there to use. So because I do have enough, what that means is that the F2 here would be my excess reagent. And by default, the nice thing about it is the sulfur would be my limiting. So once you figure out one, the other guy is the opposite. Any question on that calculation? Now, just to show you, it doesn't really matter which one you choose. So the first calculation I did, I want to use up all the sulfur, how much F2. I could also choose the opposite. So if I did the opposite calculation, which is I want to use up all of the F2, how many moles of sulfur is needed? We would do a similar calculation. We would start with our 20 moles of F2. Using our mole-to-mole relationship from the equation, 3 moles of F2 would give me 1 mole of sulfur. Moles of F2 would cancel, and I would take 20 divided by 3. Gives me 6.67 moles of sulfur is needed. In this case, if I chose that one instead of the first one, I would compare these two guys. I need 6.67. I started with 4 moles of sulfur. Do I have enough? I do not in that case, right? I need 6.67, but I only have 4. So it tells us the same thing. It tells us that the sulfur is our limiting reagent and our F2 is our excess. You do not need to do both calculations. You could just choose one or the other, but you need to do one of those calculations to determine which one's the limiting reagent. It is not always the smallest number of moles. So sometimes people go, hey, it's the smallest number of moles. It will be in a lot of cases, but it will not always be that number. So you do need to do some type of calculation to figure it out. First off, any questions on that there? Now, at this point, what I would want to do, for example, is I would then want to continue on with my limiting reagent to figure out how much product I would make. So once I did either of those calculations, I now know this guy is my limiting reagent. I would want to use the starting amount of it. So I would do 4 moles of sulfur and now do a relationship between these two guys to figure out how much product I would make. And from the equation, it is 1 mole of sulfur gives me 1 mole of SF6, which means I should produce in this case 4 moles of SF6, which would be my theoretical yield. And if I want to know how many grams that would be, I could use the molar mass of SF6 and convert it to grams. So it's really important once you figure out which one is the limiting reagent that you use the starting amount of that guy to figure out how much product you would make. Question on that there. Just to finish up here, one last thing that you could also do, which is a common question in this type of calculation, is how much of our excess reagent is left over. So if I wanted to know how much of my excess reagent is left over, I could do that based off of my calculation I used to figure out which one's the limiting reagent. We know that my excess reagent in this example is F2, and I know I started with 20 moles of F2. That was how much I started with, right? based on my calculation earlier, I calculated that I would need to use 12 moles of it to use up all the sulfur. So if I subtract those two, which is how much was needed, that would give me 8 moles of F2 should be left over. And if I want to know how many grams that was, I could use the molar mass to convert that to grams as well. So you could get lucky that you choose sort of the right one. If you didn't choose the right one that was the excess reagent, you would have to go back and maybe do the other calculation if you were asked a question like that to figure out how much of the excess reagents left over. This is a common way that you could do limiting reagents. The other common way is, just to really finish up, is just to frankly do 2 separate stoichiometry calculations. Follow the same 4 steps that we've been talking about, and you basically do each reactant to the product, just separate calculations, and whichever one produces the least amount of product is both your theoretical yield and your limiting reagent. So that's the other approach. Just 2 separate calculations, smallest one, limiting reagent, and theoretical yield. Any questions on any of that there? All right.